this lesson, we're looking at the derivatives of inverse trig functions. So in your formula sheet, you'll have the derivative of arc sine x on a as 1 over square root of a squared take x squared. You'll have the derivative of arc cos x on a as negative 1 over square root of a squared take x squared. And you'll have the derivative of arc tan x on a as a over a squared plus x squared. Essentially, in this lesson, I'm going to prove those rules for you so you can see exactly where they come from using inverse trig functions and utilizing Pythagorean identities. And in a follow-up lesson, we'll look at using these to find derivatives of different functions. So we will start with proving that the derivative of arc sine x on a is equal to 1 on the square root of a squared take x squared. Okay, so we'll start by saying that y is equal to arc sine of x on a. Now we should know straight away here that because it's arc sine x on a, or it's just arc sine, that the range of this function, so y is an element of negative pi on 2 to pi on 2. What this essentially is saying is we're only looking at positive values of cos. So it means we're looking at this side here, so we're looking at when x is positive. That will become important later on. Okay, so if y is equal to arc sine x on a, then sine y is equal to x on a, and therefore x is equal to a sine y. Now, if I find the derivative with respect to y, so I'm going to say d dy of x equals a sine y, then we end up with dx dy is equal to derivative of sine is cos, so we've got a cos y. Now, if we want to make this dy dx, we can inverse both sides, so we can flip it. So dy dx will become 1 on a cos y. Now, the final thing we have to do is deal with this a cos y. So if we look at the Pythagorean identity, we know that sine squared y plus cos squared y is equal to 1. And if we multiply everything by a squared, we've got a squared sine squared y. A squared cos squared y is equal to a squared. If we're trying to isolate a cos y, then we've got a squared cos squared y is a squared subtract a squared sine squared y. And if we square root both sides, we've got a cos y is equal to plus or minus the square root of a squared take a sine y squared. Now, remember before we said that it's only going to be positive values of cos. So that means that a cos y must be positive. So therefore, a cos y is the positive version of this a squared take a sine y squared. Final little jump here is that we've already said that a sine y is equivalent to x. So let's replace that, and now we've got a cos y is equal to square root of a squared take x squared. So now we can put this back in. We've got dy dx is equal to 1 over square root of a squared take x squared, where all values of x must be between negative a and a. So we can't end up with negative square root values there. And there we have it. We've proven what we wanted to prove, that the derivative of arc sine x on a is equal to 1 over the square root of a squared take x squared. There is our first derivative rule proved. Next thing you want to prove is that the derivative of arc cos x on a is equal to -1 on the square root of a squared take x squared. So we're going to let y equal arc cos x on a. Now, as it's arc cos, we know that y must be an element between 0 and pi, which means that sine y must be greater than 0 or it's positive. So we're looking at this section here. Obviously, sine y is positive. So again, we're going to use that later on. Now, we can invert that, and cos y will be equal to x on a, and therefore x is equal to a cos y. When we differentiate x in terms of y, we get dx dy. The derivative of cos is negative sine, and when we flip this, we get dy dx is equal to -1 on a sine y. So utilizing the Pythagorean identity again, we know that sine squared y plus cos squared y is equal to 1, and therefore a squared sine squared y plus a squared cos squared y is equal to a squared, and a sine y all squared is equal to a squared subtract a cos y all squared. So finally, a sine y is equal to plus or minus the square root of a squared take a cos y squared. Now, again, we said that a sine y must be positive, so we can get rid of the plus negative. So we have a squared take a cos y squared, and since a cos y is equal to x, as stated earlier, we end up with a squared take x squared as a sine y. Now if we put this back into our derivative, we get dy dx is equal to -1 over a sine y, which is square root of a squared take x squared. And hence we have proven what we were trying to prove, that d dx of arc cos x on a is equal to -1 on square root of a squared take x squared. There it is. We've got our proof that the derivative of arc cos x on a is equivalent to -1 over square root of a squared take x squared. Again, where x must range between -a and a. Alright, so now we're looking at our third proof. We're looking to prove that the derivative of arc tan x on a is equal to a over a squared plus x squared. So we'll take the same approach. We'll let y equal arc tan x on a, and therefore tan y is equal to x on a, and x is equal to a tan y. Dx dy, so derivative with respect to y will be a multiplied by 1 on cos squared y, and of course that means a sec squared y. If we go back to one of our known Pythagorean identities, we know that tan squared y plus 1 is equal to sec squared y. Now we've got an a in here, so we're going to make this a tan squared y plus a is equal to a sec squared y. So we'll multiply everything by a. So again, it's a Pythagorean identity application, and therefore we get dx dy is equal to a tan squared y plus a. Now we want to flip this over. So we want dy dx is equal to 1 over a tan squared y plus a. Now we've got a slight problem. What we're looking for is being able to replace a tan y with x, but we've got a tan squared y. So to solve this, we're going to multiply by a on a, so top and bottom by a. We've got a over now, a squared tan squared y plus a squared. That means we have a over a tan y all squared plus a squared, and a over x squared plus a squared is our dy dx. So again, we've achieved what we set out to achieve. We've shown that the derivative is equivalent to the given rule. So we can say that d dx of arctan of x on a is equivalent to a over a squared plus x squared, and QED. So this establishes the derivatives of arctan, arcsine, and arccos. Again, what you'll need to do mostly is be able to pick them out from your formula sheet, but understanding where they come from and the application of inverse trig functions and Pythagorean identities to the proofs of these rules should help with your understanding. Okay, that concludes the lesson. Thank you very much for listening.